Good morning, everybody. So today we will begin our discussion on chapter 3, actually. There were just a couple questions on conductors, on capacitors that we did not get to last class. So I've included those questions and the answers in the lecture notes. I hope that you will take a look at yourself. The content is mostly intro physics content for the capacitor, so there's really no need for me to do them again in class, but you can just review those questions. That would be great. So begin with chapter 3. For chapter 3, what we are doing is, as we said earlier, it's always sometimes easier to solve for the potential instead of the E field. So so it's really the equation that we're going to solve for the potential now when there is no charge density is the Laplace equation. So we'll spend our time on chapter 3 learning all these different techniques that we can use to solve Laplace equation. So that's what we're trying to do. Today, we were just going to talk about Laplace equation in general and the uniqueness theorem. And then starting tomorrow, we're going to start learning the particular techniques. Okay, so the Laplace equation is really just using the Laplacian. So that is the Laplacian of the potential is equal to 0. Okay. Now, does anybody know how do we calculate this? What would this represent?
It's just the second partial derivatives of every component.
Yeah, for this is really just a scalar function. So you're just going to take the second partial derivative with respect to x, y, and z, and that's it. Okay. So this Laplacian is going to appear in many different places in physics or engineering, just to show that what we are doing here is not just you're going to learn it one time and never use it again. You actually will see it multiple times. For example, in describing the equation describing the fluid flow, the heat equation, you can see it's a function. Laplacian describe its dependence with respect to space. At the same time, is also related to its dependence on the time, right? Similar to the wave propagation here, Laplacian described the function of distribution with respect to space, and again, they also at the same time depend on time, and those are related. Sometimes people in engineering use the velocity potential, and the Laplace equation describe the velocity potential. The potential field is very similar to what we have for electric potential. A potential scalar field describes the velocity, the flow of the liquid. And in quantum mechanics, you're going to see the Laplacian show up again in describing the Hamiltonian of a system. So you're going to see this again, hopefully in other classes. So do you still remember that the Laplace equation is a special case of Poisson's equation? If you have charge density, of course, then rho, you're just going to keep the right-hand side as rho of epsilon naught. Now, where does the Poisson equation come from? It's coming from, we know that the divergence of E is negative rho of epsilon naught. That's Gauss's law. At the same time, we also know is E is the gradient of V. Now, sometimes I would put a little thing of here on the gradient, because when you do the gradient on the scalar, you actually get a vector. So to remind us of that, we put a little vector on this delta, but sometimes you don't. You just need to know what it represents. So the Laplacian of V is the divergence of the gradient of this, which is defined as what a Laplacian is. And you can see that, well, the gradient of V is the E. So it's going to be negative the divergence of E, and it's going to be, I don't know why I'm missing a sign here. Oh, here is no sign. I'm sorry. Get a negative sign here. So that's where your Poisson equation comes from. You can see it's really just coming from what we know about Gauss's law, and really this is telling you if you have charge, the charge is going to give you electric field. That's it. So if your charge is fixed, there's always a way to find what the potential is due to such a charge distribution. And a lot of times it's very applicable when we're calculating our potential in space. So you may have a lot of charges, you have a lot of conductors around such serve as a boundary, but if you calculate potential in space, there is no density in space, and you can let the equation goes to 0 and got the Laplace equation. It's actually very useful in many different cases. So we're gonna continue to look at different ways to solve for Laplace equation. Now, before we talk about the uniqueness theorem, let's take a look at a question. So, okay, so we just talked about we can solve for Laplace equation, and I have a space. Let's say I just have some random space in the region I'm interested in. All I know is there's no charge in the space. There might be charge elsewhere, but in the region I'm looking at, there's no charge. Density is 0. What can I say about the V in the interior? So all I know is you just gave me the Laplace equation. Okay, so let's see what kind of information can we draw from that. All right, so I'll let you discuss this for a minute or two in your breakout rooms. And remember to record the screen before you go. Okay. I've got most of the votes already. Any last minute vote? Not a few seconds. Okay, I'm gonna go ahead and close the vote. C seems to be the most popular, followed by A and B. C says V is a constant everywhere in the interior. Okay, so it's all really just telling us that rho is 0 in this region. And if you think it's 0, the potential is 0 inside, can you tell us why? And if you think it's constant, can you tell us why? Or if you think there are more than those two possibilities?
I mean, I may be wrong, but I think it's 0 because if you use Gauss's law to draw some funky figure around your region, or I'm sorry, in the interior of your region, then your charge enclosed is going to come out to be 0, which leads me to think there is an electric field. So if you try and take a gradient of V, well, that's going to be equal to 0. So that leads me to think V is 0 as well.
If the E field is 0 still, even if the E field is 0, V could still be a constant. So V doesn't have to be 0. And in terms of Gauss's law, the charge enclosed is indeed 0. However, we don't know if Gauss's law is useful here. We don't know if you can use Gauss's law to calculate your E because you need the particular symmetry, right? So this is really just a space because, for example, both of us could be very well in the presence of some potential in the space right now. There's some potential around me due to some charge somewhere. But I can always find a pocket of space that has no charge, but that doesn't affect it has potential. In fact, I can give an example of, let's just pretend we have a capacitor, right? We have positively charged plate here, negatively charged plate here, and E field in between is downward, like this, parallel plate capacitor, right? And you have V, you have potential, right? That's decreasing from the top to the bottom plate. Now I can always select a region, random region in between and say, well, looking at this region, it doesn't enclose any charge. You're right, it doesn't enclose any charge. But the potential is not 0. In fact, it's not even a constant. It's a function that is in the format of like Cx plus D, sort of linearly increasing with your distance from your bottom plate, right? Because your Laplacian of this, is still 0, and a Laplacian of a constant could be 0, and Laplacian of a 0 could be 0. Or it could be even some other function, I don't know. You can always find a pocket in space that it's in space. There is no charge, but they could be charged somewhere else. So really, this may be a tricky question, but all it's telling us, tell me there is no charge in a particular region is not really telling me much. So, and also, but on the other hand, it's promising in the sense it tells us Laplace equation is so applicable in many cases. You may have charges somewhere else, but it doesn't affect me to apply a Laplace equation in the region I'm interested in. So that doesn't really tell me much at all. It's kind of, we need more information. Okay, so it's A. So further on, so there are some general properties about the solutions to the Laplace equation. Some of these are very useful. It can help us find the solution that we need for the problem that we're interested in. So we need to gather more information, and there are some general properties can be helpful. This is in your textbook. You can look at your textbook to look at the proofs around page 115, somewhere around page 115, page 117. We are simply just going to grab them and use them in class. The first properties of the Laplace equation is that the potential has no local maximum or minimum inside. If you have a maximum value for V or a minimum value for V, they can only be located on the boundary. And we'll see what that means in using a more concrete problem later. And the second point, as in Griffith's words, that V is boring, meaning that V is always continuous. If you have a V right here at the boundary between two different kind of materials, then you calculate your V function on this side of the boundary, calculate your V on the other side of the boundary, and you take the limit to be where the boundary is, and these two value better agree because you cannot have a sudden jump in your potential. So for example, if you have a solid sphere inside and outside, you may have different functions, but V cannot be a jump. Like you cannot have a V like this and then jump to something else. This point, these two has to be continuous at any given point for V. Okay, so that's the second property. The third property is if you are interested in the V, you can always find the V by looking at a surrounding sphere. So if you look curious about V at this point, you can draw a little sphere of R and then look at the V around that sphere and divide it by the area, the surface area. So part 3 is sort of a way to tell us that, oh, if you only know the V at certain point, you can always use this in expanding your area little by little, and you can always find the V at other points. So numerically, you can always do this with your computer and do programming and always find your V for all space. The fourth one is the uniqueness theorem, the first uniqueness theorem, and it's very useful. It's telling us, well, the solution to the Laplace equation is uniquely determined if your V is specified on the boundary surface around the volume. So what does that mean? That means that sometimes you don't even have to solve the Laplace equation, and you can guess a Laplace solution. So for example, if I tell you there is a region, does region satisfy the Laplace equation, and I tell you exactly V at the boundary is certain value is a known quantity or a known expression or whatever. I'll tell you exactly what V is here at the boundary. Then you can say, let me guess. If I guessed a solution V of R as a function of space, if I guess a function and it satisfy the Laplace equation and satisfy the boundary condition, then that must be the only solution possible for the potential in the region. There's no other possible ways. So a lot of cases we do guess. We say, okay, could V be this value? Well, it does satisfy Laplace. It does satisfy the boundary. Then by the uniqueness theorem, it must be the only V possible. The solution is unique. We will sort of prove this using one of the example later to prove the uniqueness theorem, to show why V is unique. So you can see we just said giving a space with zero charge density is kind of useless. It doesn't tell you anything about V. So now I'm going to give you one more information. Not only I tell you there's no charge in the space, I also tell you the V on the boundary of your region. You're interested in this region, I tell you at the boundary, V is 0, just on this black line. Okay, that's where the boundary is. And now there's one piece more information. Now can you say something more about V inside? So do you know what V is inside now? Okay, and I'll let you discuss this within your group for another couple minutes. Okay, just a few more seconds. Okay, I got all the answers now. Seems like you're in the majority of an agreement. So let me ask you guys to share your thoughts. How do you decide what V is inside the region?
I thought it was B because V being 0 around the borders kind of confirms that there's no electric fields happening on the inside.
Okay,
Would result in it being 0 everywhere.
so V is 0 at boundary tells you E is 0 inside. Is that what you're saying?
Yes, because there's no charges inside either.
So, okay, so you said, okay, E is 0 inside and so 0 everywhere inside. So that's sort of a solution you proposed to be a solution for the field. And you can conclude that must be the only solution. Could there be a other possibility?
I arrived at the same answer, but I used the uniqueness theorem. So all maximum and minimum must occur at the boundary. So if the boundary was 0, then the volume would have to be 0.
You used actually, it's a properties, that's the first properties. V has no local maximum or minimum inside. Maximum value or minimum value are located on the boundary. Yes, so by using this, there are actually multiple ways to answer this question. If you think V is not 0 inside, then V0, let's say if you think V is larger than 0 inside, then V equals 0 is the minimum. The minimum, then you have a maximum must be inside. Likewise, if using V is less than 0, then your minimum is less than 0, which is also still inside. Either way, there's gonna be a maximum or minimum that is not at the boundary, just inside, that is conflicting your first property. And 0 must be the only way to make sure that is not violated. That's very good. The uniqueness theorem, definitely. I think a lot of you probably do use the uniqueness theorem is, let me guess. I think if I guess V inside is 0 everywhere, that is one possible solution. And this solution satisfies Laplace equation? It does. Does it satisfy the boundary? Yes, V 0 inside, V at the boundary is also 0 satisfied. So both of those satisfied, then this must be the only possible solution there is. So let's prove this, right? If you're not convinced, let's try to give it a quick proof. So let me say, suppose there are 2 different V's. Suppose you don't have just one V in this region. And you know V at the boundary is given. Suppose we have 2 different possible solutions. And one is V1 and one is V2, and they're not the same, but they both satisfy the Laplace equation, which means Laplacian of V1 is 0, Laplacian of V2 is 0. Okay, they're solutions, so they must satisfy this equation. And they both satisfy your boundary conditions. V1 at your boundary is this V given. V2 at your boundary is also going to give you the value of your V given. So what I'm trying to show is that V1 and V2 cannot possibly be two things. They must be equal. So, okay, if they're not the same, let's define V1 minus V2. It's a new quantity. It's not 0, so it's a new quantity. Then V1 minus V2, this new quantity also satisfies Laplace equation because we can break this into Laplacian of V1 minus Laplacian of V2. Each of them is already 0. That's a given, right? So this is 0. So the new potential V1 minus V2 is also satisfying Laplace equation. And at the same time, we know that V1 and V1 at the boundary and V2 at the boundary are the same value. So if this V3 is V1 minus V2, if this new V3 is not 0, but some other value, then you're violating the first property. The first property is that there is no local maxima or minimum. And maximum or minimum only exists at the boundary. You can see that this is more of a general way to prove it, but we sort of already used the concrete example in a quicker question we have already kind of done that using the first properties. Then because it's violating this first property, then V3 must be 0. It cannot be a new thing. And V1 and V2 must be the same potential. It cannot be two different potentials. So here you have proof that when V1 and V2 are the same V, you have a unique solution. That is the only solution possible. Okay, so once you have V specified on the boundary, then you can uniquely decide what your V is in your region. So in real life, we're going to see some examples. Is that we're going to treat our conductors as our boundaries, and we're going to solve a Laplace equation, and we're going to uniquely decide our potential in a region by applying the boundary conditions. And then the value, the potential solution we got must be the only solution possible. Okay, so that's sort of a short proof of the uniqueness theorem. The first uniqueness theorem is the one we just saw. The solution of the Laplace equation is uniquely determined if V is specified on the boundary surface around the volume. But there's also a second uniqueness theorem. So it's like, okay, you want to uniquely decide your V. There are two ways to uniquely decide. One way is tell you what V is at the boundary. The second way is to decide, if you don't tell me what V is at the boundary, tell me some other information about the charge distribution. That's the second uniqueness theorem. The second one says, okay, you're interested in this region, and this region have multiple conductors in it. And each of the conductor have some kind of, okay, and in this inside region, you have some charge density in the space. We don't know what it is. But if you know what the charges are on these conductors, Q1, Q2, Q3, Q4, then you will be able to uniquely decide the electric field inside this region. Now, I know this sounds a little confusing, but what this is really just telling you, you need to tell me more information. You have some conductors here, tell me the charges on the conductors, and then I'll be able to uniquely decide what your electric field is. Okay, so this is a little more abstract, but we can look at a more concrete example to see how do we apply the second uniqueness theorem. So here I present this sort of distribution. Okay, so here you have a space you're interested in, and inside this space you have two conductors. This is a conductor, this is a conductor. And I tell you they're both neutral. So that is way of telling you, you know the total charge on the conductor has to be 0 overall. Okay. So, but it's not really just asking you directly, can you find your E field in this case? It's asking you, do you think this kind of charge distribution is stable in the sense that you have positive charges on one side and negative charges on the other side. And so they're both neutral conductors. Okay. You can yes or no if you're not so sure, or if you have any other answer, you can choose C. I'll let you guys again discuss this for a couple minutes. Okay, any last minute vote? Five more seconds. All right, I'm gonna go ahead and close this. Pretty much split between A and B. So this seems to be kind of a weird question, right? And you may have a good intuition, or if we don't, how could the uniqueness theorem that we just learned be able to help us? What do you think?
So I'm getting this from page 123 of the book, the last paragraph, if anybody wants to look it up. But it's basically saying if we have two conductors and the total charge on each is 0,
Mhm,
the only way for that to happen is if there's no accumulation of charge.
mhm.
That would mean that the E field is 0. So that's using the second uniqueness theorem.
Okay. So the second uniqueness theorem said if you can guess one solution and it's satisfied, the Laplace equation, also the charge is uniquely decided, then this must be the unique solution. So in your proposed solution, what do you think the potential will be, or the electric field would be inside here or here?
0.
It would be 0, right? So let's say I propose that E and V are all just 0 inside. And you can see that in the solution it proposed, if you have such a polarized distribution, then your E field must not be inside. Also, you cannot have the same potential everywhere. Like along with your direction of E, you will have a potential difference. So that means that is not a possible distribution, and your V0 is a unique solution, meaning that these charges must neutralize themselves. They cannot stay split like this. So in the case that is not a stable charge distribution, there are no other charges around. See, if there are no other charges around, and takes no work to move charges on the conductor, then these charges have no reason to not neutralize, to give you that V is 0 inside both of the conductors. So it cannot be such a distribution. And if you have such a distribution, it cannot possibly be stable. So we answer that this is no, okay? Right? Let's look at this question. Here, instead of doing, I'm gonna give you a hint that you can think about this question in analogy to the previous one with the two metal sphere. But instead we have two strong conductors and they're connected like this. The left-hand side of the conductor is connected to the right-hand side of this conductor plate, and the ones in the middle are connected. So do you think in this particular electrostatic situation, is it physically stable? The hint is think about how this might be similar to the previous question we just see, okay? All right. This one, let's not discuss. I think because of the analogy, I'm gonna go ahead and open the pool. If you want to, you can take a minute to think before you put in your results, okay? Okay, I'm getting most of our votes already, so just a few more seconds. If you haven't voted, please put in your vote. All right, I'm gonna go ahead and end this. So this is our result distribution. So how do we even begin to process this? Anybody would like to tell us what they think? Is this particular charge distribution, could it be stable in the sense it will stay like this for a long time?
I'm thinking that the electric field is only in between the two conductors, so
Okay,
there's nothing else like interfering with anything, so it should be stable.
electric field would be what, only in between?
Yeah, so like in between, like on the minus and plus on the left conductor, and then the minus and plus on the left conductor, on the right conductor.
Oh, you mean like in between, like in here?
Yes.
Okay. So you're supporting answer E as stable or non-stable?
It's stable.
Okay, so let's think about this. If you have sort of a parallel plate capacitor, I agree. If you don't have any of this, if you don't have this, you don't have this, you just have those two plates. Obviously, the positive and negative charge would come closer to each other, right? But the thing is, as soon as you connect this with a metal wire, as soon as you connect this with the metal wire, you have rearranged your distribution to be two conductors. This one, this negative Q, and this wire along with this positive Q, they become one. They become like a one conductor, big conductor. And what's inside, the positive Q and negative Q here and the wire inside, make them become one piece. You know, they shaped like three pieces, but they're connected. They're becoming like one piece. So you can think of this question, now they have really changed into two pieces of conductors. And we argue that one of the piece is split. Another piece is also split. Isn't this the same question as we did before? It was two metals here, and they each are neutral overall, right? Carry zero net charge, but the charges are split. So this is just the same as our previous question, right? For that reason, the total charge here is zero, total charge here is zero. And I propose and I argue E here must be zero. Let's say pretend you don't agree with me. Let's say you think, oh, E0 is only one possible solution because that satisfies your Poisson equation. E0, V0, that satisfy your Poisson equation, Laplace equation, or you can say it's satisfied with Gauss's law, whatever. And that's really just one solution. But the second uniquely theorem saying, if I could guess a solution and it is satisfying the Laplace equation and the charge distribution is given, then this must be the only possible solution. There couldn't be another possible solution. So I argue E must be zero inside, V is zero inside as well. And these charges cannot possibly be polarized like that. And this question is just like the previous one. And it's therefore cannot be stable. Okay, so it's still not stable. The trick is to look at these conducting plates connected as if they're one piece. This one, however, I'm not going to let you vote on this one, but I do want to talk about this one, is if you get rid of the wire on the outside and just leaving the wire inside, then this is certainly okay. Now, this case is as if you have a conductor, capacitor parallel plate capacitor, negative Q here, positive Q here. And what's inside, you have just inserted a metal slab in between. So this become a one entire piece. So this just become a piece inside. And you insert a piece inside a parallel plate capacitor, because of the polarization, now positive goes to one end, negative goes to the other end, and it's polarized. And in this case, it is stable, it is okay. But as soon as you connect this piece to this piece, then everything is going to neutralize. They're not going to be stable anymore. Okay. Now, one last question before I solve some examples together with you guys. This is one last clicker question. Here you have these 8 point charges. They're sitting at this sort of looks like a lattice, each of the corner of the cube. You put a positive charge test Q in the middle. Do you think that it could be in stable equilibrium in the middle? Think about what it means to have a stable equilibrium, meaning that even if you shift it a little bit, it can always be shifted back to the center. It's kind of like you're in the dip of the hill and it's hard for you to climb out of the hill valley. All right, so this one, do discuss within your group for a couple minutes. Okay, I gathered most of the votes already, just 5 more seconds. Okay, I'm gonna go ahead and close the vote now. This is our results. The answer, the majority think that it is possible to have a stable equilibrium if you put a little test charge tube in the middle. So with this symmetry, right, I think you would agree with me that it is possible to balance out the forces, to balance out the electrocoulomb forces on the little test charge Q. But is it going to be in stable equilibrium in the sense that if it's shifted away from the center by a little bit and it will still come back? What do you think?
So I said no, and I got this from again from the book from Earnshaw's theorem. But my reasoning was I think it has something to do with number 3 and the general properties of solutions to Laplace's equation,
Okay.
where I think the voltage at some point is the average of, like if you draw a Gaussian sphere around all your charges, that it should be equal to the average potential over that surface. So I
Okay.
feel like it has something to do with that.
Okay, yes. So the Earnshaw theorem, we'll talk about that in a minute here. Let's think about how we could argue this using the uniqueness theorem. So what does a stable equilibrium suggest? That if you have a sort of something like this, potential like this, and your little ball in here, that's stable equilibrium. It's hard to get out of the well, right? So a stable equilibrium suggests that the electric potential of this little test charge Q is Q times potential, the volts, potential energy is Q times potential, must be at the minimum in the middle, right? So that is stable equilibrium suggests. So that means my potential must be a minimum in the middle. And is that a problem? If I draw a little, so here is my middle. If I can draw a little area around it, you can see that if this is a minimum, that's a problem because the minimum only exists at the boundary, not the local area. So if I sort of surround it by any little surface, you can see this will be the area, the boundary of my area, but not a random point in the middle. You can see that it violates the first property of the 4 properties we talked about, and therefore you're not going to have this minimum value in the middle, only at the boundary. So it cannot be in the stable equilibrium. Okay, so as soon as you shift away from the center, it's not going to be staying there, not going to go back in there. And that is what we call a Earnshaw theorem, saying that you cannot have a stable equilibrium for a charged particle by the electrostatic forces alone. Given that Earnshaw theorem, it's really interesting that how the crystals are stable, that tell us that quantum mechanics matters. If you only look at electrostatic forces, you cannot hold this charged particle in the middle in the static equilibrium state. That's what Earnshaw theorem is telling us. Okay, and you can explain this by using the idea of no local minimum or maximum except at the boundary to argue. Okay, all right. So that's all of these conceptual questions. Next, coming up, I want to solve one example just to show that how do we decide the potential within the space by solving Laplace equation and by applying the V values at the boundary, because that's what we're trying to do in this chapter. So here I'm showing you with an example. First of all, let's draw a picture of the 2 conducting area. So here you have a conductor here on the left-hand side, and this conductor is grounded. And you're keeping a potential difference between this plate, between this conductor and another conductor on the right-hand side. And the potential difference you kept is V naught. And the distance between them is D. And the question is, what is the V in between? Can you solve for V in between? All right, so I'm gonna point my X and Y and Z in these directions. So we're trying to solve the Laplace equation. So in between the conductors, there is no charge. Therefore, the Laplace equation applies in the gap. And here, my conductors, you can see, is infinitely large in the Y and Z directions. So I argue that my potential in between the gap is only going to be depending on the X direction. It's not going to change with Y or Z. Does that make sense? It doesn't change, it doesn't depend on Y, meaning that if you're looking at a point here versus a point a little bit inward, it's going to have the same V because your conductors is large in the Y direction. Also, it doesn't depend on Z. If you look at a point here or a point a little bit above, you're going to deal with the same potential. Okay, so it doesn't depend on Y or Z, but only depend on X. So the Laplace equation becomes really simple. This used to be the 3 dimensions, but now since it doesn't depend on Y and Z, all I really need to do is to solve this equation. This is what I need to solve. So V is V sub X. Okay, so I know this. What other information I know? I also know boundary conditions. So before I solve everything, I want to lay out the boundary conditions that I do know. So V at X equals 0, here at X equals 0 on the left-hand side is grounded, so V is 0. V at X equals D on the right-hand side, that equals D, is kept at this constant potential V naught. So that is V naught on the right-hand side. Those are your 2 boundaries. So I have those 2 boundary conditions, I wrote it down. Okay, so solve for Laplace equation and match it up with your boundary conditions is sort of the general process we will go through. So let's solve this. This is just one dimension, right? So that's easy, relatively easy to solve. So this is 0, which means dv dx must be a constant. So let's say it's a constant, we call it c. So v would be a linear function with respect to x. So v must be c times x plus another constant d. Okay, so I have solved the general expression for v in the middle in between these 2 conductors. And now let's apply the boundary conditions. So let's apply the first one. V at x equals 0 is 0. So c times 0 plus d is 0, which means d is 0. Let's apply the second one. C times d plus 0 is v naught. And that tells what this constant is. C is v naught over d. Okay, so I've solved my 2 constants. The potential in the middle is simply v naught over d times x. And that's it. This is my potential in the middle, these 2 conductors. So what do you think that, what do you think this represents? What kind of physical setup do I have? What is this physically? A capacitor, thank you, Nicholas. It is a parallel, it looks like a parallel plate capacitor, right? A large plate. And these large plates are infinite in y and z directions. And you're looking for the change of your potential in the x direction, right? So you just had, this is turned out just to be a capacitor with E field is pointing in this direction, right? And the potential from left to right-hand side increase linearly with your space. So it turned out this is just a capacitor, and we have solved it using a Laplace equation and our boundary condition. So you can see our V is continuous because you take what V you solved in the middle and you match it up to the left-hand side of the boundary and match up. You match it to the value of the right-hand side of the boundary, it also matches up. There shouldn't be any jump in your potential solution or your value. So this is for V specified at the boundary. A lot of times they don't give you the potential at the boundary, but they give you the charge density at the boundary instead. And that is also okay. You can also solve for V if they give you the charge potential at the boundary. Why is that? Because if they don't give you the V, you cannot match up V, but if they give you charge density, so for example, the same problem, now instead, if I don't give you V, don't give you the V for this one. I tell you, I give you a charge distribution, and again, everything else is the same, X and Y, and Z, the distance D in between. You know that, well, because this charge distribution, we can know what E is right outside of the surface. So if you use Gauss's law here, we apply Gauss's law. You will find E is sigma over epsilon naught. Again, the sigma over epsilon naught, true epsilon naught, because this is conductor. It's different from an insulator equation. To pointing to the left, right here, you have your E in this direction. And E is related to V. So because the gradient of V is negative of E, so the gradient of V in this case is really just the gradient is 1D because V is one dimensional. dV is only changed depending on X. So dV over dx is a gradient and apply it at the boundary. So you can see you cannot match V directly at the boundary, but you can match up the derivative V at the boundary. Okay, so this is another way to do this. So dV over dx is negative E. So E is negative X, so positive sigma over epsilon naught. So if I do V is going to be a general solutions of Cx plus D, and V x equals 0 is 0, I got D equals 0. So V is Cx, and you plug it here, taking the derivative, you get C is equal to sigma over epsilon naught. Okay, so you really solved V as well, is sigma over epsilon naught times X, and that's your solution. So whatever your left wall is, your right hand side of the wall is going to be a higher potential than your left hand side. So if your left wall Vx equals 0 is 0. Now, if your left hand side is V naught, then this will be this value plus V naught. Okay, so this is for if the left wall is grounded. But if it's not grounded, we just add whatever the left wall is. Okay, so either they give you V at the boundary or not, they give you the charge density of at the boundary. Either way, you can find your potential. So there are two. So the boundary conditions are often given in two of these ways. Boundary conditions. They either tell you what V is, or they will tell you what dV dN is. dV dN, what does that mean? N is the area vector that is perpendicular to the surface. So V dV dN is taking the derivative in the direction of your surface area, the area that is perpendicular to your surface. In this case, the n is your x. If you have a surface like this, and this is your n hat. Okay, so either they give you v or they give you the derivative of v with respect to n, and you can uniquely find your potential. And you will be able to find the inside the region you're interested. There are two boundary conditions sometimes are given in this format. So in this case, we won't have time to do this in class, but I want you to go ahead and review this on your own. Remember previously, we had talked about there is no, if you have a surface and you do sort of the line integral, still remember this, around a surface, right? You should get E dot into dl is 0. So, which means E parallel up and E parallel below should be equal. This will derive E parallel above is equal to E parallel below. That ensures your closed integral is 0. So that is one boundary conditions for the E field. Another boundary conditions, it has to do with the perpendicular. And a lot of times, instead of writing what the E is, that give you derivative with respect to V. So another boundary condition is given in this format. The potential derivative with respect to n above a boundary minus this below a boundary is equal to negative sigma over epsilon. This is equivalent to E perpendicular above a boundary minus E perpendicular below a boundary is negative sigma over epsilon. Because E perpendicular to the surface, right? E perpendicular to the surface is in the direction of the n hat. So they either give you this or they give you this, they're the same. So to sum up, the parallel component of E is always continuous across the boundary, but the perpendicular component of V can jump. So that's why sometimes when you're drawing the field for E, you could have a sort of a sudden jump from this to here. And that indicate that must be a perpendicular component of E, but not a parallel component of E. But overall, E can jump across the boundary but not V. V is always continuous. V is always smooth everywhere. So this, I want you to go back to your book and make sure you read the book and see the derivation for this particular question. We sort of did a really quick derivation for the first one, but we didn't do the second one. So make sure you read and do your book on the second, okay? All right, I'm sorry I went over a little. I'll see you guys today at your office hours. If not, I will see you on Friday at our recitation. All right, have a good rest of the week, everyone.
Thank you, Professor. You too.
Thank you.